When you look at the night sky far from city lights, you can see thousands of stars with just your eyes. In fact, there are many more stars in the sky too faint for us to see. Each star that you can see is part of our galaxy, the Milky Way, our celestial home that has captivated the attention of people for centuries, the attention of humanity for centuries. The bright band of stars, dust, gas, and dark matter captivates us in the night sky. All these elements are held together by gravity, and as we navigate through the cosmos, an intriguing enigma arises. What is the Milky Way really like? What composes it? And where is our solar system located within it? Astronomers have been puzzled by these fundamental questions for many centuries, and finding answers has not been easy. But beyond its luminous beauty lies a tapestry of mysteries waiting to be unraveled. Join us today on this incredible adventure through the Milky Way to discover its mysteries, wonders, and majesty. You are probably somewhat familiar with our solar system. At a minimum, you probably already know that it contains 8 planets, in addition to Earth, the Sun, the moons, and various other celestial bodies such as asteroids and Pluto. However, there's much more beyond the solar system that you may not know. From Earth, we can see approximately 6,000 stars without the need for a telescope. Although it seems like a large number of stars, it represents a very small portion of the total. In fact, for every star you can see, there are more than 20 million. Most of the stars are too faint to see, they are too far away, or they are obstructed by clouds of cosmic dust. While the Milky Way contains all these stars, there are also other larger galaxies, such as the Andromeda Galaxy. Each galaxy is a system made up of various stellar remnants, interstellar medium, and stellar systems. Astronomers believe there are 100 billion galaxies in the cosmos, but they are not sure. Intergalactic space, which contains a thin gas, is located between galaxies, given the size of our solar system, and the fact that only one of many in our galaxy. It is understandable that the universe is thought to be infinite. This really helps put into perspective how small both Earth and human beings are in the big picture. Through the use of radio telescopes and X-ray telescopes, scientists have been able to collect information over the last century about the composition of the interstellar medium. They have shown that it is made up of extremely diffuse ionized hydrogen atoms, dust, and cosmic rays scattered through dense clouds of gas that are believed to be the birthplace of new stars. However, due to the Sun, the 8 planets, and a distant disk of debris known as the Kuiper Belt, its exact nature just outside our solar system remains largely unknown. The Kuiper Belt is located between 30 and 50 astronomical units from the Sun. 1 astronomical unit is equivalent to the distance between Earth and the Sun. The heliosphere, a huge protective bubble created by the solar wind, surrounds them all. This bubble collides with the interstellar medium like an invisible shield that keeps most of the dangerous cosmic rays and other materials away, while the Sun and the planets around it rush through the galaxy. Without the heliosphere, life would undoubtedly have evolved differently and perhaps would not even have existed. The area where the magnetic bubble of the Sun ends and weakens is known as the border of interstellar space. The heliosphere, a magnetic bubble filled with plasma or ionized gas, the solar wind, which pushes away the lines of the Sun's magnetic field, propels material into the heliosphere with its own magnetic fields and charged particles. The plasma of the interstellar medium exerts an inward pressure on the edge of the heliosphere, creating a complex and dynamic structure there. When the solar wind comes into contact with interstellar space, it begins to weaken and slows down to a speed of approximately 100 kilometers per hour, when it previously traveled between 600 and 700 kilometers per hour. The termination shock is the point at which this occurs. The heliosheath zone is the area of the heliosphere in which the solar wind continues to slow down after the termination shock, while the heliopause is the outermost edge of the heliosphere, where the solar wind stops and gives way to interstellar space, which is located about 11 billion miles or 18 billion kilometers from the Sun. Music 5, 4, 3, 2, 1, ignition. We have left it since the beginning of human space exploration. Only 2 probes have reached interstellar space, the area outside the solar system. After its launch in 1977, Voyager 1, the first spacecraft, took more than 30 years to reach the pores of Helia, a boundary that scientists believe marks the beginning of interstellar space. It was an incredible achievement to send vital information through a medium unaffected by the Sun. Upon leaving the solar system, we will reach Alpha Centauri, the triple star system closest to Earth, located approximately 437 light-years away in the constellation of Centaurus. It is a triple star system made up of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri AB is a binary star system made up of Alpha Centauri A and B, which are stars similar to the Sun, classified as Class G and K, respectively. These 2 main stars have an apparent magnitude of -0.27, which makes them appear as a single star to the naked eye. Only Sirius and Canopus are brighter than it, making it the brightest star in the constellation and the 3rd brightest in the night sky. Alpha Centauri B is smaller and colder than Alpha Centauri A, with a mass of 0.9 solar masses and less than 0.5 solar luminosity. While Alpha Centauri A has 15 times the luminosity and 11 times the mass of the Sun. The 2 have an orbital period of 79 years around shared center. The distance between A and B fluctuates from 356 astronomical units, approximately the distance between Pluto and the Sun, to 112 Australian dollars, approximately the distance between Saturn and the Sun, due to the eccentricity of its elliptical orbit in the Alpha Centauri system. Proxima Centauri is the closest star to the Sun, located approximately 42 light-years from Earth. Robert Innes, a Scottish astronomer, discovered the star in 1915. Proxima Centauri is a red dwarf star, which is the most common type of star. It is approximately 7 times smaller than the Sun and a little more than half as hot, with 3,100 Kelvin. On the other hand, our Sun has 5,772 Kelvin. In fact, this star is only 50% larger than Jupiter. Red dwarf stars have long lives because they consume hydrogen very efficiently. Proxima Centauri is expected to remain in its current state for over 4 trillion years. Although the Alpha Centauri system can be seen in the constellation of Centauro, Proxima Centauri is not usually visible to the human eye. Proxima Centauri orbits the other 2 stars of the Alpha Centauri A and B system. Proxima Centauri takes 550,000 years to complete an orbit around A and B, with an apparent visual magnitude of 11. Proxima Centauri is the faintest of the 3 stars. This star emits light at a slower rate than the Sun, with a luminosity that is 0.17% of the Sun's. However, Proxima Centauri is classified as a flare star, prone to massive solar flares, as its brightness can vary by more than 1 magnitude in a matter of minutes. These eruptions, which occur several times a day, can be so powerful that they make Proxima Centauri visible to the human eye. The largest solar flare ever observed in the Milky Way was emitted by Proxima Centauri in 2019, shining 14,000 times brighter in ultraviolet wavelengths than normal. Although Proxima Centauri will live longer than the Sun, it will suffer the same fate. Proxima Centauri will end up as a burning white dwarf star because it does not have the mass necessary to become a neutron star or black hole when its hydrogen supply runs out. As of 2022, astronomers have detected 3 planets orbiting Proxima Centauri, B, C, and D. These are the closest planets beyond our solar system. Red dwarf stars are small and cold, so planets can orbit quite close to them and still be classified as habitable. This is the range of distance from a star in which the water of a planet can be liquid and, therefore, harbor life. Proxima Centauri b was discovered in 2016, and it is estimated that the planet contains approximately 177% more mass than Earth, so it is likely that it is also a rocky planet. Proxima Centauri b is still within the habitable zone of Proxima Centauri, despite being much closer to its star than Earth is to the Sun. It orbits Proxima Centauri every 11 Earth days, at a distance of approximately 0049 AU, more than 20 times closer to Proxima Centauri than Earth is to the Sun. It is very likely that Proxima Centauri b is synchronized like our Moon, with one face always facing its star, given that it is much closer to its star than Earth is. Therefore, it is possible that liquid water exists on the opposite face, but its habitability is unknown due to extreme radiation and the eruptions of its host star. Proxima Centauri b feels the gravitational attraction of its star much more strongly than we feel the effect of the tides of our Sun here on Earth. The Moon exerts more tidal force than the Sun because it is much closer, and the tides not only attract the ocean but can also move the air. It is possible that the force of the tides in the atmosphere of Proxima Centauri b is up to 500 times stronger than that of Earth's atmosphere. It is likely that Proxima Centauri b is approaching the maximum tidal force a planet can withstand and still retain its solid surface. However, the climate and weather conditions of Proxima Centauri b are not mostly affected by its extremely high tides. Located just outside the habitable zone, at around 15 astronomical units from the red dwarf, is the exoplanet mini-Neptune Proxima Centauri Ca, which is about 7 times larger than the Earth and orbits its star once every 1900 Earth days. Discovered in 2019, this superplanet appears to shine much more than expected for its size, indicating that it may be enveloped in dust clouds or surrounded by a ring system. The estimated temperature of the planet by astronomers is extremely cold, probably close to minus 233 degrees Celsius, which makes it uninhabitable due to its distance from its star and its large mass. The gravity of Proxima Centauri caused the speed of its parent star to falter, leading to its initial detection in 2019. In 2020, images from the Hubble Space Telescope from 1995 were used to confirm the existence of Proxima Centauri SE. Therefore, it is one of the few exoplanets with visual confirmation. In 2022, a third planet was discovered around Proxima Centauri. The exoplanet, known as Proxima Centauri d, orbits its star at a distance of approximately 3% of Ley and contains approximately 25% of the mass of the Earth. Proxima Centauri d completes an orbit around its star every 5 Earth days. Due to its relative proximity to it, it is among the lightest exoplanets that scientists have observed so far. In addition, in 2021, scientists detected what could be the first indications of an exoplanet orbiting Alpha Centauri, also known as Rigel Curis, in the habitable zone of the stars, called Candidate C1. It is estimated that C1 has a mass between half that of Saturn and Neptune and orbits Alpha Centauri at a distance of approximately 11 Australian dollars using direct thermal images. C1 was found with an elongation of around 0.1 arc and appears to be as bright as a giant planet, agreeing with the orbital movement of a planet in a 70 degrees orbit. The fact that C1 is in the habitable zone of Alpha Centauri A and that it may be a mini-Neptune or a super-Earth makes the discovery of this exoplanet much more interesting. We are almost certain that there are Earth-like planets in Alpha Centauri, but the main question is, could human beings live there? Music. The most difficult obstacle in our search for a new home in the Alpha Centauri system would undoubtedly be to travel an enormous distance to reach these 3 stars. Despite the fact that Alpha Centauri is the closest star system to Earth, is still more than 4 light-years away, which is approximately 235 trillion miles or 378 trillion kilometers. To cover such a large distance, we would need a much faster spacecraft or other means of transport. NASA claims that the Discovery Space Shuttle, which was retired in 2011, had a maximum speed of about 17,500 mph, but even at this constant speed, it would take more than 148,000 years to reach Alpha Centauri. NASA estimates that, even when the Orion spacecraft, the crew capsule linked to the Artemis program, is ready to transport people, its maximum speed will be approximately 32,000 kilometers per hour, which will not significantly reduce the travel time to Proxima Centauri. Even if any of these vehicles were designed to travel outside the solar system instead of making relatively short trips to the Moon or Mars, as we have already discussed, the only spacecraft that have left the solar system so far are Voyager 1 and Voyager 2, And even at their maximum speed of more than 35,000 miles per hour, it will take them almost 40,000 years to travel 2 light years to reach the indistinct border between Proxima Centauri and our solar system. That implies that these spacecraft could take more than 880,000 years to get close to the star. After all, it takes light over 4 years to reach Alpha Centauri. To reach a distant star in a reasonable time, such as within a generation, a spacecraft would have to be extremely small and robotic. In addition, it would need an incredibly strong energy boost to reach the necessary speed, and that is the basic concept of the Breakthrough Starshot project, to create a nanonave equipped with a solar sail called Starship that would be sent to Earth orbit. The mothership would launch the tiny probes one by one, which would then be placed in the rays of a colossal set of ground-based lasers. However, the main challenge is the Earth's atmosphere, which distorts the laser and incoming light and makes it difficult to apply the force necessary to propel a spacecraft. Much more powerful lasers on land could maintain a tight focus on the space mission thanks to small lasers mounted on satellites that would evaluate the atmospheric impacts in real time to send the ship at any moment. The necessary lasers require an astonishing power of 100 gigawatts, which is equivalent to the total electricity consumption of the United States, but they only need to operate at full power for 10 minutes. They plan to employ 100 million lasers to distribute electricity in an area of 1 square kilometer. The Starshot team is determined to push the limits of space exploration. When the lasers turn off, the object that travels through space will travel at an impressive speed, 20% of the speed of light, more than 130 million miles per hour or 216 million kilometers per hour, with a diameter of just over 10 meters. This spacecraft could reach Alpha Centauri in about 22 years, but could be significantly slowed by the sun's gravitational attraction and interstellar debris. The ship's signals will take 4 more years to reach Earth, even after they reach Alpha Centauri. Alpha Centauri is moving towards Earth, but very slowly and does not pose an immediate cause for concern. The distance between Alpha Centauri and Earth in 2024 is approximately 326 light years. It will reach its closest point in the year 29,700 DC, when it will be about 3 light years away. Throughout the life of a human being, the slow change in distance will not have an appreciable impact on Earth or the solar system. Space is an extraordinary place from which we learn new things every day. Leaving behind Alpha Centauri, we travel towards Barnard's star, the second closest star to the Sun, at a distance of 595 light years. It is named after Edward Emerson Barnard in honor of the American astronomer who discovered it in 1916. With an estimated age of between 11,000 and 12,000 million years, approximately twice that of the Sun, Barnard's star is an ancient star and, most likely, a member of the Milky Way's thick disk. Young or middle-aged red dwarfs usually rotate fast enough to produce powerful magnetic fields that can lead to eruptions that quickly double the brightness of a star, but Barnard's star is too old to show this type of behavior. However, on July 17, 1998, Diane Son and her colleagues at NASA's Goddard Space Flight Center revealed that Barnard's star had emitted a flare similar to this at the time the star spectrum was obtained using the 27M telescope of the McDonald Observatory by William Cochran of the University of Texas at Austin. Their hope was to find alterations that pointed to the existence of planets in orbit, but instead he saw emission lines in the spectrum that indicated that the star could be 4 years later. The Cochrane team's research revealed that the star's hot blue flare was similar to those of younger red dwarfs, even though it was quite old. The temperature of the flare was at least 8,000 Kelvin, more than twice the temperature of the star, which was 3,100 Kelvin. As Barnard's star approaches us, its distance decreases by 36 light years each century, at an incredibly fast speed of 108 kilometers per second or 67 miles per second. Its maximum approximation to the Sun will be at a distance of only 385 light years in the year 11,800 DC. In terms of proper motion, Barnard's star is also the fastest moving star in Earth's skies. Another characteristic that makes Barnard's star unique is that it has the highest proper motion of all stars, approximately 104 arcseconds per year, which is equivalent to the lunar diameter every 180 years. For this reason, and its relative proximity, is an ideal target for the search for exoplanets, since any systematic variation in its movement through the sky caused by orbiting planets would be more perceptible. Finally, in 2018 a planet was found around Barnard's star. The planet orbits the star at a distance of approximately 60 million kilometers or 37 million miles in a 233-day orbit with a mass at least 32 times greater than that of Earth. The planet is not in the habitable zone due to the low brightness of the star, and any water on its surface would probably be frozen as we move away, about 86 light-years away. Near the constellation of Orion, we find Sirius, also known as the dog star or Sirius A, which is the brightest star in Earth's night sky. With a mass twice that of the Sun, Sirius has a diameter of 15 million miles or 24 million kilometers. Sirius would eclipse our Sun by more than 20 times if it were located next to it within the constellation of Ursa Major. Sirius is a binary star. The name of the star comes from the Greek word Syros, which means bright or burning, with a surface temperature of almost 18,000 degrees Fahrenheit. Sirius has a bluish hue and is 25 times brighter than the Sun. It is clearly visible in the winter night sky of the northern hemisphere. The ancients were familiar with Sirius due to its extreme brightness. However, astronomers were surprised when Sirius B, a companion star, was discovered in 1862. The star is visible to the naked eye, while Sirius B is 10,000 times fainter than Sirius. Thanks to data from the Hubble Space Telescope, astronomers were finally able to estimate the mass of this faint object in 2005. Even though it is extremely difficult to observe from Earth less than 20 light-years from the Sun, there are about 131 objects, including stars, brown dwarfs, and sub-brown dwarfs. Only 22 stars are bright enough to be seen without a telescope, which means that their visible light must be at least 65, the lowest brightness that can be seen with the naked eye from Earth. The 131 known objects abound in 94 star systems, of which 103 are main sequence stars consisting of 23 typical stars with a higher mass and 80 red dwarfs. In addition, scientists have discovered 21 brown dwarfs, a sub-brown dwarf, Y085507114, which is possibly a wandering planet, and 6 white dwarfs, stars that have exhausted all their fusible hydrogen. A red dwarf candidate, known as Schultz's star, and a companion brown dwarf passed near the edge of the Oort cloud about 70,000 years ago. At this time, it is about 22 light-years from the Sun, and is likely to have triggered a comet storm that will take more than 1,000,000 years to reach the inner solar system. The objects of the Kuiper Belt were affected by its passage. Other stars have also been investigated, such as the G-type star HD 7977, which passed nearby about 28 million years ago and is currently about 247 light-years from Earth. Of course, past interactions are not the only thing to consider, as there will be more stars in the future. In the next 15 million years, 694 stars are projected to approach the solar system to a distance of less than 516 light-years. According to data from the second publication of the Gaia telescope, 26 of them are likely to reach less than 33 light-years, and 7 more to less than 6 light-years due to the large number of stars that must be studied. This number is probably much higher. For example, a star that was approaching the solar system 10 million years ago would today be at a distance of between 606,000 light-years from the Sun, while there are now millions of stars closer to the Sun. Gliese 710, an orange star about 60% the size of the Sun, is located in the constellation of Serpens. This star is heading towards us at a speed of 5,499 kilometers per hour, almost 32,000 miles per hour. In 129 million years, it will pass in front of the Sun at a distance of about 10,520 Australian dollars, more than 100 times the distance of Pluto, which orbits the Sun at an average of 395 Australian dollars. But it still has the potential to alter the solar system if humans are still on Earth at that time. We do not have to worry about any alteration of our orbit, since if Gaza 710 has any effect, it will only have on the outer solar system and should not have any impact on anything within 40 astronomical units, but still could cause alterations in the Oort cloud, since it has a very high probability of crossing it during millions of years. This would cause showers of comets heading towards the Sun, which could lead to approximately 10 comets being seen with the naked eye each year. The search for stars close to the Sun could not only be an opportunity to find ancient comets, but also to predict an intriguing future for Earth observers in millions or even thousands of years. The local interstellar cloud, which is about 30 light-years in size, is where the solar system and other stars and dwarfs are now moving within or near. The local interstellar cloud is in turn contained within the local bubble, a cavity in the interstellar medium about 1,000 light-years in diameter and with a strange peanut shape. Our Sun was very far away when the bubble formed 14 million years ago, but about 5 million years ago, the Sun's path went into it. Interestingly, stars formed on the surface of the bubble, but not inside. There are 7 star-forming regions around this bubble. Thanks to this local bubble, life is possible on Earth today. As we move away, we will reach the constellation of Orion, about 1,344 light-years from Earth. A light-year is the distance that light travels in 1 year, about 6 trillion miles or 10 trillion kilometers. The constellation of Orion is one of the 88 modern constellations and is named after Greek mythology. It contains more than 60 stars, including Betelgeuse, a red supergiant located about 650 light-years away. This is one of the largest stars known, with a diameter of about 767 million miles or 12 billion kilometers, about 700 times the size of the Sun, and has a mass between 10 and 20 times that of the Sun. Because a Betelgeuse may have less than 300 years of fuel in its core, whether or not it will explode has been continuously debated around the world. The core of the star will collapse into a black hole as it burns its last drops, expelling the outer layers of the star at speeds of up to 25,000 meters per second or 40,000 kilometers per second. Astronomers refer to this fiery disappearance as a supernova explosion, and, in the case of Betelgeuse, it will be an impressive spectacle for Earth observers. Those layers of gas and dust will shine in our sky for several weeks with a brightness comparable to that of the full moon, since the star is only 650 light-years from Earth. The problem is that most astronomers do not believe that Betelgeuse is ready for a big explosion yet. Astronomers normally expect it to explode in the next 100,000 years or soon on a cosmic, not human, timescale. The other famous stars in this constellation are located on the line of the belt of Orion, which consists of 3 stars around the center of the constellation. These are Alnitak, Alnilam, and Mintaka from east to west. The belt is perhaps the most recognizable feature of Orion, as it is visible worldwide. These 3 supergiant stars, separately, are thousands or tens of thousands of times brighter and several times more massive than the Sun. Even though these stars appear closer to each other in the sky, they're actually very far apart. The belt of Orionth belt of Orion is mainly used by astronomers as a celestial reference point to search for M42, also known as the Nebula of Orion. M42 is located below the belt and is one of the most visible Messier objects for beginner astronomers, as it is easy to locate and observe with a telescope or binoculars. Looking at it is like looking at a celestial nursery where new stars are born. It is one of the largest clouds of gas and dust in our Milky Way. Galaxy is the nebula of Orion, which is approximately 2 million years old and is located about 1,300 light-years from Earth. Because the magnificent nebula has an apparent brightness of +4, it is visible even to the naked eye on the astronomical magnitude scale. +6 is the faintest object that, in the best lighting conditions, is visible to the human eye. This huge nebula, which has a diameter of between 30 and 40 light-years, could be giving rise to the birth of thousands of stars. Within the nebula is a young and open star cluster whose stars are still very weakly connected by gravity after forming together in the cloud of gas. It is sometimes referred to as the star cluster of the Orion Nebula. In 2012, an international group of astronomers suggested that this cluster of the Orion Nebula could have a black hole in its center. Through small telescopes, you can see the four brightest stars of the Orion Nebula, known as the trapezium. The Orion Nebula is illuminated by the light of the young and hot stars of the trapezium. In terms of stellar life, these are young stars with an approximate age of 1 million years. Last year, the James Webb Space Telescope took an infrared image of the Orion Nebula. It shows an explosion of dust, stars, and clouds in shades of red, purple, and blue against a background of dark space. In addition, James Webb has discovered 540 objects with planetary mass, with masses ranging from 0.6 Jupiter masses to Jupiter's own mass. Among these planetary mass objects, the most fascinating are the Jupiter mass binary objects, which are separate objects orbiting in space on their own. Our galaxy, the Milky Way, is a spiral galaxy. A spiral galaxy is a galaxy that looks like a flat, rotating disk with a bulge in the center and spiral arms extending outward from it. Although there are many minor arms and only 2 main arms in our spiral galaxy, astronomers used to believe that there were 4 main arms. Scientists have discovered that only 2 arms that wrap around the ends of a central bar of stars dominated. These discoveries were possible thanks to NASA's Spitzer Space Telescope, using infrared images. The 2 main arms of the galaxy, Scutum Centaurus and Perseus, are visible at the ends of a thick central bar, while Norma and Sagittarius, the 2 secondary arms now degraded, are located between the main arms and are less distinctive. Although the secondary arms are mainly composed of gas and zones where stars form, the main arms have the highest density of young and old stars. Radio astronomers use large telescopes to study the movements of those hydrogen clouds that trace the arms with an angle of inclination of about 9 degrees. The Perseus arm has a spiral extension and measures more than 60,000 light-years in length and 1,000 light-years in width, and has the well-known Crab Nebula, in addition to double clusters. On the other hand, the Centaurus arm measures about 55,000 light-years in length and 1,000 light-years in width. Our solar system is located between 2 prominent spiral arms, the Perseus arm and the Centaurus arm. However, we do not float completely free in empty space, but are located on the edge of the Orion arm, sometimes called the Orion spur or local arm, which is a small spiral arm. This spiral arm is about 10,000 light-years long and 3,500 light-years in diameter, although a 2016 analysis indicates that its length could exceed 20,000 light-years. The Orion arm is named after the constellation of Orion. The solar system is located in the local bubble on the inner edge of the Orion arm, about 26,000 light-years from the galactic center, halfway along the length of the Orion arm. You may be surprised to know that the Sun takes 250 million years to complete one rotation around the Milky Way. This is known as a cosmic year or galactic year. Therefore, during its life, it is estimated that the Sun has only completed between 18 and 20 orbits. Since the beginning of humanity, the solar system has orbited the Milky Way at a speed of about 220 kilometers per second, or 0.73% of the speed of light. The solar system takes about 1,400 years to travel 1 light-year at this speed, or 8 days to travel 1 astronomical unit following the ecliptic. The solar system travels towards the zodiacal constellation of Scorpio. The last time the solar system was in this position in the Milky Way, dinosaurs still existed on Earth. Who knows when it will happen again? Humanity could be extinct or could have evolved into something completely different. Our place in the galaxy is important because it seems that galaxies have habitable zones, just like planetary systems. Since many of the orbits of the suns of the Milky Way, the Sun orbit the galaxy following trajectories that take them through the deadly spiral arms, and an amazing 95% of them may not be suitable for hosting habitable planets. Since the radiation from stars so close to each other is deadly to any planet that passes through one of these stellar swarms. To maintain its alignment with the rotation of the galaxy, our solar system orbits far enough from the galactic center to remain in the Karma region. between the spiral arms within a large and complex galaxy. The Earth and its sister planets are well located in a quiet and resource-rich region. As we approach the center of our galaxy, the Milky Way, located about 9,500 light-years from Earth, in the constellation of Cecilo, we will reach Uae, considered one of the largest stars known, with a radius of 1,180 million kilometers, 1,700 times greater than the radius of the Sun. This would give the star a diameter of more than 8 astronomical units, which is equivalent to 8 times the distance between the Earth and the Sun, or 150 million kilometers, or 93 million miles. Due to the immense size of this hypergiant star, its outer surface would reach far beyond Pluto, which is about 5 times further from the Sun than the Earth. The gas nebula that the star expels extends 400 times the distance between the Earth and the Sun, far beyond the orbit of Pluto. Or, seen another way, more than 1 million Earths could fit in the Sun, but about 5 billion suns could fit in a sphere the size of Oiscuti. It is not surprising that Oiscuti is classified as a hypergiant star, the classification that comes after supergiant and normal giant. Although it may be the largest due to its size, but is not the heaviest or the most massive. The term mass in massive refers to the amount of matter in the star. The heaviest star is our 136A1, which weighs about 300 times the mass of the Sun, but only about 40 times the radius of the Sun. On the other hand, Oiscuti is significantly larger than the Sun, although it only has a mass between 7 and 10 times that of the Sun. Similarly, being so massive does not mean that Uae is so hot. In fact, its surface is almost half as hot as that of our Sun. Another thing that makes Uae particularly interesting is the fact that it is a variable star over time. Variations in luminosity can be observed as a result of the continuous fluctuation on and near the surface due to the unstable struggle between the forces of gravity and fusion. These stars are of particular interest to astronomers because they can shed light on the inner workings of stars. Although it is believed that Oiscuti, like many other stars, is capable of sustaining a planetary system, the innermost exoplanets may have already been engulfed by the expansion of the host star. In addition, Oiscuti is so faint that it is unlikely that we can see those exoplanets directly. As we delve into the center of our galaxy, the Milky Way, about 26,000 light-years away, we see a celestial enigma, Sagittarius A star. This supermassive black hole is a cosmic monster that escapes our understanding. Sagittarius A asterisk is not just any black hole. Its estimated mass is 43 million times that of our Sun. Imagine compressing millions of suns into a single point, a gravitational singularity where space and time are warped beyond recognition. This massive monster is located in the heart of the Milky Way, our spiral galaxy. A black hole is a region of space so densely packed with mass that nothing can escape from it, not even light. Black holes are invisible to us, but telescopes can see the material around them. The matter surrounding black holes, which may consist of gas and dust, heats up and releases detectable radiation. In some cases, telescopes can observe the gravitational influence of a black hole on the movement of nearby stars. Observing it directly is a formidable challenge. Sagittarius A asterisk is hidden by a dense layer of dust that prevents optical observations. However, astronomers have developed clever strategies to break through this cosmic curtain. The Event Horizon Telescope, a network of radio telescopes spanning the planet, made history in April 2019 when it managed to obtain the first image of a black hole. This discovery occurs after the EHD collaboration published the first image of M87 in 2019, the black hole at the center of the distant galaxy Messier 87. Sagittario A was visible in the photograph as a diffuse outline against a bright background. This turbulent region, known as the accretion disk, feeds matter to the hungry black hole, causing occasional X-ray flashes. Despite the fact that Sagittario A is less massive and over 1,000 times smaller than M87, the two black holes are quite similar. The gas disk that surrounds them, extending to a distance of between 5 and 30 light years, can reach temperatures of up to 18 million degrees Fahrenheit or 10 million Celsius. The supermassive black hole at the center of our galaxy not only rotates, but does so at almost maximum speed, consuming everything in its path. Physicists use NASA's Chandra X-ray Observatory to study X-rays and radio waves from material outputs in order to measure the rotation speed of the supermassive black hole of the Milky Way. The rotation speed of a black hole is represented by the letter A and varies between 0 and 1, where 1 is the maximum rotation speed of a specific black hole and represents a significant fraction of the speed of light. Physicists discovered that Sagittario A rotates at a speed of 0.84 to 0.96, which approximates the upper limit determined by a black hole's width. The spin of a black hole differs from that of other celestial objects. Black holes are regions of space-time defined by a non-physical outer limit called the event horizon, beyond which light cannot escape. Unlike planets, stars, and asteroids, which are solid objects with physical surfaces, this implies that, when rotating, black holes literally distort space-time itself, dragging everything within the ergosphere. This phenomenon, known as frame dragging or the Thirring lens effect, implies that knowing the rotation of a black hole is necessary to understand how space acts around it. In addition, the frame dragging around black holes produces strange visual effects. The path of light twists or curves as it approaches a rotating black hole due to the rotation of space-time. This causes a process known as gravitational lensing, in which the gravitational force of the rotating black hole deflects the path of light. Frame dragging effects can lead to the production of light rings and even a black hole shadow. These are examples of how light is affected by the gravitational force of black holes. The theoretical maximum speed of a black hole is determined by how it feeds on matter and, therefore, how it grows. As matter falls into a black hole, the black hole's spin increases, but there is a limit to the amount of angular momentum it can possess. The mass of black holes is another factor. The gravitational attraction of more massive black holes is stronger, making it more difficult for them to rotate. This could explain why the rapidly feeding supermassive black hole at the center of the galaxy M87, the first black hole captured by a camera, rotates at a speed of between 0.89 and 0.91 despite having a mass of 65 billion suns, while Sagittario, with a mass equivalent to about 45 million suns, has a rotation speed of between 0.84 and 0.96. But something strange soon happened while investigating this black hole. Some scientists believe that Sagittario A may not be a black hole at all, but an immense concentration of dark matter. Imagine a dark pool of invisible matter that forms the basic structure of our galaxy. Sagittario A has never been directly confirmed, even though it is widely believed to be a black hole. Simply put, it is an extremely bright radio emitter located in the Milky Way's galactic nucleus. The astronomical community encountered a difficult problem. G2, a galactic cloud, had gotten too close to Sagittario A. The G2 gas cloud continued to drift without undergoing notable changes, even though the supermassive black hole should have attracted and destroyed it. The observation of the interaction between Sagittario A and the gas cloud G2 revealed that G2 was not an ordinary gas cloud as seen by the lack of effect, that at least two components had to be present to allow the cloud to pass so close to the black hole without being devoured. One is an extensive, cold, and low-mass gas cloud, and the other is a very compact segment, similar to a dusty object, that dominated the detected emission from G2 as it passed. However, astronomers may be more concerned about the possibility that Sagittario A is not actually a black hole. First, scientists created a simulation of our galaxy because they were intrigued by the idea that the center of the Milky Way could actually be a mass of dark matter. The researchers found that, despite the replacement of the galactic center, the Milky Way continues to exist and functions basically the same way in all simulations. The behavior of the rotation curve in the outer halo of the Milky Way was identical to that of nearby stars, or those connected to the radio source Sagittario. Taking their research one step further, they proposed that the darkos, a family of particles related to fermions, could constitute the mass in the center of the Milky Way, apart from its extreme characteristics, such as devouring everything around it. Darkos would have the same properties as a black hole if they were grouped into a huge mass. Sagittario A is mostly inactive and only occasionally absorbs gas or dust, but nevertheless has an estimated mass millions of times that of our Sun, although there are still many unanswered questions about the future of the supermassive black hole. Future observations from the Event Horizon Telescope should shed more light on these enigmas. Stellar mass and intermediate mass black holes are formed when massive stars stop performing nuclear fusion and can no longer sustain themselves against total gravity. The mechanism that forms supermassive black holes like Sagittario A is unclear, as there are no stars large enough to collapse directly into a black hole of this size. There are two possible explanations. Either smaller black holes merge to form larger black holes, or smaller black holes grow enormously by consuming gas and dust from their surrounding Sagittario. It remains an astronomical wonder, a cosmic mystery at the heart of the Milky Way. As we deepen our understanding, we continue to unravel the secrets of our galaxy. In 1917, the American astronomer Harlow Shapley provided the first reliable measurement of the galaxy's size. He determined the size by first determining the spatial distribution of globular clusters, as had previously been believed. Shapley discovered that the galaxy is enormous, with the Sun closer to its periphery than to its center, rather than a relatively compact system, which assumed that globular clusters surrounded the galaxy. He calculated that the galaxy is approximately 100,000 light-years, or 600,000 trillion miles in diameter. The Sun is located approximately 30,000 light-years from the galaxy's center. His values have remained remarkably accurate over the years. The stellar disk of the Milky Way is about the size predicted by the Shapley model. Dark matter or invisible matter may occupy a larger volume than expected, while neutral hydrogen is somewhat more distributed. According to recent calculations, a zone of dark matter that includes some visible stars could have a diameter of about 2 million light-years. In addition to having multiple satellite galaxies, the Milky Way is a member of the local group of galaxies, which is a subcluster of the Virgo supercluster, which in turn is a component of the Laniakea supercluster. Music. There are at least between 100,000 million and 400,000 million stars in our galaxy, and at least that many planets. The Milky Way and everything else in space is in motion. The radiation from the Big Bang, known as the cosmic microwave background, is used as a reference to calculate the speed of objects in space. The Milky Way is believed to travel at a speed of approximately 600 kilometers per second or 372 meters per second within the local group of galaxies. Since the oldest stars in the Milky Way are almost as old as the universe, it is very likely that they formed shortly after the Big Bang. Music. Dark ages. The galactic nucleus is where a wide range of activities, apparently driven by the black hole, takes place. The region emits X-rays and infrared light, and clouds of gas can be seen moving rapidly. The data clearly show that matter, including some gas from the Z direction, perpendicular to the galactic plane, is being drawn from outside the nuclear zone into the black hole. As the gas approaches the black hole, the strong gravitational force of the central object compresses the gas into a rapidly rotating disk that extends outward between 5 and 30 light-years from it. Around the nucleus is an extended bulb of stars that is almost spherical and mainly composed of population 2 stars, although they are relatively rich in heavy elements. The metallicity of a star, or the amount of elements heavier than helium in its composition, divides the stars into 3 main groups. Those of population 3 are the oldest, and those of population 1 are the youngest, like our Sun. The disk part of the galaxy contains the population 1 stars, whose ages range from 0 to 10,000 million years. The spiral arms include the youngest stars. The orbits of the population 1 stars are well organized with approximately circular trajectories in the mean plane of the galactic disk. Young star clusters formed by population 1 stars are called open clusters because the stars are weakly bound to each other, unlike the old concentrated globular clusters. Compared to population 2 stars, population 1 stars have a higher abundance of elements heavier than helium. Astronomers frequently refer to elements heavier than helium as metals. The oldest population 1 stars have somewhat eccentric orbits that can take them up to 3,000 light-years from the plane of the disk and have a metal abundance of 0.1 times that of the Sun. Population 2 stars inhabit the spheroidal component, the stellar halo, and the bulge. They have masses less than or equal to 0.8 solar masses, and, being old, their ages range from 10,000 to 13,000 million years. Their orbits are much more randomly oriented than those of population 1 and are very elliptical. As a unit, the spheroidal component has little global rotation. Population 2 stars form globular clusters. Globular clusters were used to find the center of the galaxy because they swarm around it like bees around a hive. On the other hand, population 3 stars are those that have not been directly observed. They are believed to have virtually no heavy elements. These stars are believed to have been the first to form in the early universe, shortly after the Big Bang. They were extremely massive and hot, and burned their fuel very quickly, converting hydrogen and helium into heavier elements. When they die, they explode as supernovas, scattering some of these elements into the surrounding space. These stars likely created the first heavy elements that were part of later stars and played a key role in the formation of the first galaxies. Numerous globular clusters of related stars mix with the stars, and both the stars and the clusters orbit around the nucleus in an almost radial way. Our galaxy is surrounded by a huge halo of hot gas that is several 100,000 light-years in diameter. A halo is a spherical cloud of stars that surrounds a galaxy. The mass of the halo is believed to be approximately equal to the total mass of all the stars in the Milky Way. Astronomers have proposed that the halo of the Milky Way is composed of 2 populations of stars. Findings from the Paranal Observatory indicate that the stars in the inner halo are 11,000 million years old, while the outer halo appears to be made up of stellar components from smaller galactic systems. The stars in the halo are older and have a lower metal content than most of the stars in the disk of the Milky Way. The halo also contains gas and dark matter. The halo is evidence of the collision of 2 galaxies billions of years ago and reinforces the idea that the Milky Way has a dynamic origin. In the stellar halo of the Milky Way, astronomers have also found more than 200 distant variable stars, known as RR Lyrae stars. These stars serve as important standard candles that are used to measure astronomical distances and are often found in globular clusters. The farthest star from Earth is located approximately 1 million light-years away, which is almost half the distance to Andromeda. Around 90% of the matter in our galaxy is dark matter, that is, matter invisible to the human eye. Stars make up the remaining 10 to 15% of the visible matter in the Milky Way, which is mainly composed of gas and dust. Simulations of the rotation of the Milky Way have shown that this enormous amount of dark matter produces an invisible halo. If dark matter did not exist, the stars in the Milky Way would orbit much more slowly than has been observed. The dusty ring of the Milky Way can be observed in the night sky on a clear night. As we are about 26,000 light-years from the Milky Way center, we cannot capture images of the disk. Any representation of our galaxy that you have seen is an artistic interpretation or a separate spiral galaxy. We only have an image of the Milky Way as a whole, since we can capture images of it from within the galaxy. So why do we believe it is a barred spiral galaxy? Music, there are several clues. The first clue about the shape of the Milky Way comes from the bright band of stars that stretches across the sky in dark night skies. This band of stars can be seen by the naked eye. That band comes from seeing the disk of stars that forms the Milky Way from within the disk and tells us that our galaxy is basically flat. Many telescopes, both on Earth and in space, have captured photographs of the Milky Way's disk capturing a sequence of images in different directions, which is similar to creating a panoramic photo with a phone or camera. The concentration of stars in a band adds to the evidence that the Milky Way is a spiral galaxy. If we lived in an elliptical galaxy, we would see the stars of our galaxy scattered throughout the sky, not in a single band, music. Until about a century ago, the Milky Way was believed to be only a few thousand light years in size, and most people believed it was the entire universe. Although other galaxies have been found, they were believed to be just small objects within our galaxy. The French astronomer Charles Messier discovered the first galaxies in the 17th century, although at that time, he had no idea what they were. As an expert comet observer, Messier saw several additional blurry objects in the sky that he was sure were not comets. Fearing that other comet hunters would also misidentify them, he compiled a list to help them. On Messier's list, 110 star clusters and spiral nebulae were detected. The objects are designated with the letter M for Messier, followed by a number, for example, M51. However, it took astronomers almost 300 years to decipher the diffuse spiral nebulae. Some claimed that these nebulae were island universes, objects similar to the Milky Way but existing outside it. Others disagreed and thought that these spiral objects were actually clouds of gas from Milky Way. The dispute continued until the 1920s, when American astronomer Edwin Hubble measured the precise distance to a spiral nebula. Hubble discovered that one of the objects he was seeing was actually a Cepheid variable star. In 1923, while studying the Andromeda Nebula, now known as the Andromeda Galaxy, first identified in the early 20th century by American astronomer Henrietta Leavitt, she discovered a connection between the luminosity or brightness of a Cepheid and its period, which is now known as the period luminosity, PL, relationship. The PL relationship can be used to calculate the actual brightness of a Cepheid star by calculating its period, which is obtained by measuring the changes in brightness over a period of days or weeks. Hubble established that the Cepheid star he was studying in M31 was outside our own galaxy by calculating its distance using the PL relationship. This ended the controversy surrounding spiral nebulae and proved that they were actually distant galaxies similar to the Milky Way. Hubble continued his study of galactic distances using Cepheid stars as a measurement tool before publishing his results in 1929 in his work. Hubble created a graph showing the distances of the Cepheid variables and the velocities of the galaxies, obtained from estimating the redshift of these galaxies. According to this graph, most galaxies are moving away from us or receding, and their speed of movement, the recession velocity, is inversely proportional to their distance from us. The more distant galaxies move away more rapidly than the closer ones. This later became known as Hubble's law. Hubble's initial estimates for the recession velocity of galaxies were very high, because at that time no one knew that there were actually several different types of Cepheid variables with slightly different period and luminosity relationships. But as astronomy has recently advanced, the value of the slope of the graph, known as the Hubble constant, and the results now converge towards an accepted value of about 65 kilometers per second. That is, that galaxies move away an additional 65 kilometers per second for each megaparsec. They move away from us. There are trillions of galaxies in the universe, and in each galaxy there can be up to a few 100 billion stars. Just as atoms are studied to understand the qualities of a material, the basic components of the universe must be studied to understand it. Understanding the formation and evolution of galaxies is essential to our understanding of the universe. Although the study of galaxy formation dates back about 50 years, with the fundamental works of Egan Lindenbell and Sandage, we still do not have a complete understanding of how galaxies form and evolve. There are still many details to explore, in addition to providing us with valuable answers to questions such as where we come from and where we are going. Observing other galaxies, in addition to our own, also allows us to draw several conclusions about the evolution of the universe. But the only galaxy for which we have a large amount of data about its stars is our own. The other galaxies are too far away for us to observe them star by star. Before continuing, one might wonder if the knowledge of the Milky Way provides us with any information about other galaxies. The answer is yes. Approximately 50% of the stars in the modern universe reside in galaxies similar to the Milky Way. In other words, the Milky Way is a fairly faithful representation of a typical galaxy in the universe. Our knowledge about the evolution of the Milky Way will provide us with a solid basis for understanding other galaxies. Music. Shortly after the Big Bang, which took place 136 billion years ago, the Milky Way began as one or more small excess densities in the mass distribution of the universe. Some of these excess densities were the seeds of the globular clusters in which the oldest stars remaining in what is now the Milky Way formed. Approximately half of the material in the Milky Way may have originated in other distant galaxies. These groups of stars and individual stars now form the stellar halo of the Milky Way. The mass of the Milky Way reached a point where it began to rotate relatively rapidly, only billions of years after the birth of the first stars, due to the conservation of angular momentum. This caused the gaseous interstellar medium to compress into a disk from an approximately spheroidal shape. Therefore, subsequent generations of stars formed in this spiral disk. Throughout its history, the Milky Way has consumed many galaxies to reach its current size and shape. In the last 12 billion years, the Milky Way has engulfed more than a dozen galaxies. According to cosmological simulations, it merged with a particularly massive galaxy known as the Kraken approximately 11 billion years ago. Our galaxy is currently consuming the Canis Major dwarf galaxy, adding its smallest stars to its own spiral. Currently, the Milky Way travels at 250,000 miles per hour in the direction of the Andromeda Galaxy. It is expected that the two galaxies will collide in approximately 45 billion years. The Via Lactea and Andromeda are the two largest galaxies of the local group and will merge because they were gravitationally bound to each other before dark energy took control. The merger is expected to change Earth's night sky. The Milky Way orbits a point in space approximately halfway between it and the Andromeda Galaxy. Although it is difficult to believe, experts think that our solar system will probably survive such a terrible event, since galaxies are mainly composed of empty space. This collision will not significantly impact our solar system, despite each having 100 billion stars. Our galaxy and the Andromeda Galaxy are very far apart. Currently, Andromeda is 25 million light-years from Earth, similarly to how a ball in the air accelerates faster when falling towards Earth. Andromeda will be attracted faster and faster by the gravitational force of the Via Lactea as it approaches. In just 4 billion years, the Milky Way and Andromeda will have pushed and torn each other, and all that will remain is the spectral framework of two galaxies. In the past, the butchery continued while time did not stop, until the central supermassive black holes of both galaxies were close enough to collide and join. At that time, the Milky Way and Andromeda galaxies, the two separate spiral galaxies, will cease to exist. Our solar system will have a new home in a completely different type of galaxy called an elliptical galaxy. What will then happen with life on Earth? Will life on Earth continue after the merger? Well, in approximately 75 billion years, the Sun will grow larger and swallow Earth, turning into a red giant. This will ultimately happen within about 4 billion years, as the solar radiation reaching Earth increases. The surface temperature of the Earth will increase, and we could experience an uncontrolled greenhouse effect very similar to the one that is happening right now on Venus. So there's a good chance that life on Earth will not exist after the merger. However, perhaps by then, some people on Earth will have developed the ability to travel in space. We may have abandoned Earth and our solar system by then. The view of Andromeda colliding with the Milky Way could still be within our reach, although from a slightly different angle. As we look up, let us be aware of how short our life is. We are stardust contemplating cosmic history. For some reason, we are here, sitting and wondering about the universe. We, the children of the universe, born from ordinary chemicals billions of years ago, contemplate without the black and infinite abyss and think about it.